Good morning, friends. How are you? So, in this video, I just want to find, or I just want you to make familiarize with the concept of electric field due to a conducting sphere. So, basically the conducting spheres are of two types. So, there are two types of conducting spheres. So, conducting sphere consists of charges. So, these two conducting spheres are basically two types. One is hollow conducting sphere. Hollow conducting sphere means there is no material inside this sphere. It is an empty sphere. So this is called as an hollow sphere. Sometimes we'll call it as shell. A spherical shell or a hollow conducting sphere. And the second one is solid sphere. So the conducting spheres are of two types. From this what we can understand? The conducting spheres are of two types. One is the solid conducting sphere and the hollow conducting sphere. In these two spheres, the charge, as they are conducting spheres, in these two conducting spheres, the charge is distributed on the surface. The charge is distributed on the surface. Either it may be a solid sphere or it may be a hollow sphere. The charge is distributed on the surface. So what I need to know, or what I want to find is the electric field. The electric field due to a conducting sphere. The electric field due to a conducting sphere consists of hollow as well as solid. It may be solid as well as hollow. Now I just want to show you how we can find the field. See, the reason why I am making this video is for GATE examination, for many competitive examinations, it is very important to know the field in different regions of a conducting sphere. You may encounter many number of questions on this topic. That's why I want to make a video on this topic. Means the electric field in a conducting sphere, or the electric field of a sphere. The electric field of a conducting sphere. So just now we have seen there may be hollow conducting sphere, or there may be hollow conducting sphere or a solid conducting sphere. Now how can I find electric field of a conducting sphere? See, instead of going through the different formulae, I just suggest you to go through the laws that are helpful in finding the electric field. Now here I am considering a sphere. It may be hollow or solid. Now the charge is uniformly distributed on the surface of the sphere. So I am considering a positive charge that is uniformly distributed on the surface of the sphere. Now for a sphere, how can we find the field? In order to find the field, we need to consider all the regions that are related to this sphere. What are the regions that are related to the sphere? One is the region which is inside the sphere, means this is the region, and another region is the region which is outside the sphere. So how can you represent the region inside the sphere? For example, if the radius of this sphere is r is nothing but the radius of the sphere. Now how can you differentiate the region which is inside the sphere and the region which is outside the sphere? So the region which is inside the sphere can be represented with r less than r. R is nothing but the region, the radius of the region, or the radius of the spherical region which we are considering. And capital R is nothing but the fixed radius of the conducting sphere. If R is less than R, we can call it as inside sphere or inside spherical region. If r greater than r, we can call it as outside sphere or outside spherical region. So see, we can understand in a simple way. If the radius which we are taking is less than the actual radius of the sphere, we can call this region as the region inside the sphere. If the radius of the spherical region which we are considering is greater than the radius of the conducting sphere, then we can call it as the region outside the sphere. Now, for these two regions, we need to find the electric field. So how can we find the electric field for these two regions? One is the region inside the sphere and the region outside the sphere. The technique that we are following, or the law which we are following here, is Gauss Law. Gauss Law is used to find the field for different regions here in a spherical conductor. So in the first case, I am considering R greater than, I am considering the region R greater than capital R. So R greater than capital R. Now, how can you show R greater than capital R? If this is the conducting sphere where the charge is uniformly distributed like this. Now, what is the radius of the sphere actually? Capital R is nothing but the radius of the sphere. Now, if I consider a region outside the sphere, which is outside the sphere, this is the region outside the sphere, and I want to take what is this? This is called as the Gaussian surface, because in order to apply Gauss law to find the electric field, we need to select a Gaussian surface which is symmetrical to the conducting object. What is the conducting object? A hollow sphere or a solid sphere is the conducting object. Now, how can you select a Gaussian surface for this conducting sphere? It is another sphere with radius less than that conducting sphere or greater than that conducting sphere. So, what is this radius? This radius is smaller. The Gaussian surface, the radius of the Gaussian surface is smaller, and capital R is nothing but the radius of the conducting sphere. Now, how to find the field due to this? If I assume the charge Q is distributed uniformly on the entire surface of the solid conducting sphere, if I assume the charge as Q, how can we apply Gauss law? What is Gauss law? Gauss law states that the total charge enclosed in a closed surface is equal to the total flux leaving the closed surface. So, total flux leaving the closed surface, I am assuming this as psi. It is the electric flux. Now, it must be equal to Q according to Gauss law. And what is this? The total flux leaving the closed surface. So, D dot ds. Now, how can I find this? See, what is the charge enclosed Q? So, according to Gauss law, Q is equal to. Now, how can I find this integration? See, when you have the charge like this, you have the field which is in radial direction. See, this is the field which is in radial direction from the surface of the conducting sphere to the Gaussian surface. From the surface of the conducting sphere to the Gaussian surface, or through the Gaussian surface, the field is in radial direction. Hence, I can select d bar as dr ar bar. So, dr is nothing but the radial component of d bar, and ar bar is nothing but the unit vector. Now, how can I select a surface which is in radial direction? See, I want to know what is the flux leaving through this area, or through this area, or through this small area, or through this small area. So, what is the surface direction? Surface vector direction is always perpendicular to the surface. If this is the surface vector direction is this. If this is the surface vector direction is this. So, here also the surface vector direction is this. Now, when you observe, the direction of the surface vector as well as the direction of the field, both are same in case of a solid sphere. Now, how can I select ds bar? So, ds bar must also be selected in radial direction. For a sphere, we need to consider spherical coordinate system. So for this we have made a video how to select the differential length, differential surface and differential volume in different coordinate systems. In spherical coordinate system, how can I select ds bar in radial direction? Simple. If you want to know ds bar in radial direction, just keep the unit vector ar bar, and what are the remaining components, theta and phi. So already r is covered. The variation in theta can be written as r d theta, and the variation in phi can be written as r sin theta d phi. So you will get r square sin theta d theta d phi ar bar. This is the surface vector in radial direction, and this is the field in radial direction. Now you need to consider these two in order to find the flux or the field. See, if you know the flux density, you can find electric field intensity by just writing the relation E is equal to d by epsilon. That's why I am using Gauss law. Now surface integral means double integral. So this integration is in terms of, this is theta and this is phi. So theta is equal to 0 to pi and phi is equal to 0 to 2 pi. For a complete sphere to form, you need to consider theta from 0 to pi and phi from 0 to 2 pi. So it is dr ar bar dot r square sin theta d phi ar bar. So ar bar dot ar bar is 1. You will get the dot product as 1. And for this integration, dr is constant and r square is also constant. You can take it out. So from this, I can write q is equal to dr into r square. You can take it out from the integration. Now integration of sin theta is minus cos theta within the limits of 0 to pi, and integration of d phi is phi within the limits of 0 to 2 pi. So you'll get dr into r square, and this comes out to be 2, and this is a 2 pi, so q. So dr is equal to q by 4 pi r square. So 4 pi r square you can directly write without doing this integration, because as you know the radius of the sphere as as you know the area of the sphere as 4 pi r square, just dividing that with the flux. Flux is nothing but the charge according to Gauss law. So if you divide this with flux, you will get q by 4 pi r square directly. So this is dr. So now how can I find er, which is also in radial direction? E is nothing but d by epsilon, so er can be written as q by 4 pi epsilon naught r square. So this is the field for a region which is outside the sphere, because the radius r is considered as greater than capital R. So this region is outside the sphere, and if you observe this expression, it looks like a point charge. Means if we observe the electric field due to a point charge, it looks similar to that. So that you can easily remember the expression of the field outside a conducting sphere, which may be hollow sphere or a solid sphere. Because in a hollow sphere or a solid sphere, the charge is uniformly distributed on the surface. When you inject a charge on a hollow sphere or solid sphere, it is distributed uniformly on the surface. Now what is the another region? Another region is r less than capital R. So r less than capital R is nothing but, for example, if this is a sphere of radius capital R, considering the charge is uniformly distributed on the surface. Now I want to consider a Gaussian surface inside the sphere. This Gaussian surface must have the radius of r. So now this is the Gaussian surface. What is the Gaussian surface? This is the Gaussian surface of radius r. Why we are considering the Gaussian surface inside the sphere? Because I want to know the field inside the spherical region. In the previously we have determined the field outside the spherical region. Now we are finding the field inside the spherical region. Now how can you find the field? See, according to Gauss law, psi is equal to q is equal to surface integral of d dot ds, means the total flux these two related to total flux. The total flux leaving a closed surface, this is the closed surface, Gaussian surface, is equal to charge enclosed by that surface. Now when you consider this Gaussian surface which is shown with dotted lines, the total charge enclosed, Q enclosed for this Gaussian surface is 0. There is no charge enclosed by this Gaussian surface. As this Q value is 0, D value is also 0. As D is equal to 0, E is also equal to 0. So now what we can understand from this is, for a conducting sphere which is a hollow or solid, there is no electric field inside the sphere. You have only the electric field outside the sphere. Now we got two fields. One is inside the sphere and outside the sphere. Just I want to write here, for r less than r, what is the field? E bar is equal to 0. Similarly, for r greater than r, what is the field? E bar is equal to, we got this as q by 4 pi epsilon naught r square a r bar. This we need to remember in mind in order to find the field due to a conducting sphere. Now if I draw a graph, means if I draw the variation of the field on a graph with respect to radius, I want to show the variation of the field like this. Here I am considering r is equal to capital R as the boundary. So this is the surface of the sphere, and what is this region? This is the region inside the sphere, because here r is less than r. Okay, what is this region? This is the region outside sphere, because this is the region which is for r greater than capital R. Now what is the field? What is the field expression? See, I want to show on the y-axis the field and on x-axis the radius, the field variation with respect to radius. Now if I want to know the field exactly at capital R is equal to R, how can I get? It is E is equal to Q by 4 pi epsilon naught capital R square. This is the maximum amount of field which is exactly on the surface. So this is the surface, R is equal to R is the surface. So for the region inside the sphere, the field is 0. So this is the field variation, the field is 0. Now exactly at R is equal to R, you will have the field maximum. What is this value? This value is Q by 4 pi epsilon naught capital R square. So from R is equal to 0, what is this value? R is equal to 0 means from the center to the surface, the field remains 0. Now exactly at the surface, the field suddenly increases to this value, which is equal to Q by 4 pi epsilon naught R square. Now when we move beyond the surface, for the region outside the sphere, if you observe the E by, as the charge on the conducting sphere is constant, 4 pi is constant, epsilon naught is constant, E is proportional to 1 by R square, or E is inversely proportional to square of the radius, R square of the distance from the center. So the E value reduces like this. So this is the variation. So the variation looks like this. So this is similar to the gravitational force of Earth. Gravitational force of Earth inside the, if this is the Earth, inside the Earth, this is the region inside the Earth, the gravitational force is 0. Whereas on the surface of the Earth, you have the maximum gravitation. And when we move far away from the Earth, the gravitational force reduces. Similarly, you got the electric field. So in this way, you can understand the electric field due to a conducting sphere, whether it may be hollow sphere or solid sphere. This concept will be very much useful in finding the potential inside a conducting sphere, or the potential outside the conducting sphere, what is the field inside the sphere. Like that you may get different questions in competitive examinations. So I request all of you to go through this video completely, and thank you very much for listening to this video. If you really like this video, please share and subscribe among your friends, and I request all of you to watch this video completely. Thank you very much.